Data does not move very fast by itself. You need to make data work. And Joe Armstrong said, which I'm sure we'll hear again very shortly, that first you make it work, then you make it beautiful, and only if you really have to, make it fast. It's my distinct honor to present two presenters that will talk to you about what you need to do when you need to make things fast. So without further ado, the individual who taught me Erlang, which it is a distinct honor to actually be introducing one's teacher, Marc Sugiyama and Niko Tsikoudis. Welcome.
All right, thank you, everyone. So we're going to, Robert was saying, we're going to be talking about how do you, when you have to, how do you make something go faster? So we'll start by, wait, it's not moving. There we go, nope, too far. There we go. All right, so we've all heard this quote from Joe Armstrong about, oh yeah, we're not seeing the slides here. I don't know if there's something we can do about that. Yeah. Yeah. Okay. So, well, for the people here, those of us here, but first, Joe Armstrong would often say, first make it work, then make it beautiful, and if you really have to, you make it fast. And usually, if you make it beautiful, then it's going to be fast enough. I think it's a great sentiment, and we do follow this. But the challenge with this is, what does beautiful really mean, right? It requires having a certain aesthetic or a certain intuition about what beautiful code is really like. And depending on where you come from, what language maybe you came from before you got to Erlang, that aesthetic might be different, and it may not really exactly match what Joe Armstrong had in mind when he said, make it beautiful. And so for those of us who don't have as much experience with Erlang, we need some tools, and we need to learn what that intuition should be and what that aesthetic is. So part of this presentation will be about our journey towards having a better understanding about what beautiful code is. So just to make it easier to understand what we'll be talking about, I just want to briefly introduce what we do at Datometry and what our product is. So the product is called HyperQ, and at a very high level, you can think of it as a kind of gateway. And what we do is that we allow applications that are written to talk to one kind of database, talk to a different kind of database. So in particular, we allow clients that were written to use Teradata talk to cloud data warehouses like Google BigQuery or Azure Synapse. And so in order to do that, we have to do two things. The first thing is that we have to emulate the network protocol that Teradata clients use, right? And the second thing we need to do is we have to translate the SQL, because the dialects of SQL are different. There can be mismatches in the kinds of data types that are allowed, and differences in behavior even with the SQL. So this talk is primarily about the network protocols. And so we have to, in order to emulate the network protocol of Teradata, we also have to take the results that we get back from the cloud database and translate that data into the correct format, right? And all of this, the translation of the protocol and the SQL translation adds overhead to the processing of a query. And it's in this overhead where we found some performance challenges.
So for the rest of the talk, we'll see some lessons we learned while working on a customer incident, where we observed some significant overhead as part of HyperQ. The customer is a large retail organization, and they have some pretty strict SLAs for report generation. Typically, they generate these reports by running some SQL queries that go to cloud database engine through Hyperq, and they produce a large output. Now, one day, the customer realized that one of these queries could complete on the cloud database engine within a minute or so, but there was a 4-minute gap from the time the query was complete on the cloud database engine until the client received the results back from Hyperq. This particular query returns 6 million rows, 20 columns per row. This is more than 300 million elements in total, and the size was about 2 gigabytes. So we typically start working on these incidents by having in-house reproduction. We create a similar environment with the same cloud database engine. We generate a similar amount of data, and we use a similar client to run queries through Hyperq. So it's important to know that Hyperq will receive the data from the cloud database engine, and it will split the data into multiple chunks, and the chunks will be converted in parallel. Hyperq converts multiple chunks in parallel before sending the data to the client. So what we typically, the first thought that typically comes to our mind in this kind of situation is what will happen if we provide more resources to Hyperq to increase the resources that Hyperq can use to convert data. So we try to scale up and double the number of cores that Hyperq could use. However, we realized that the benefit from doubling the cores was low. We saw a less than 50% improvement, and the cost can be high. Doubling the resources can lead to paying twice as much to the cloud provider. Now, something that was kind of surprising to us was a limiting factor for this was hyperthreading. We get 64 cores, but these are virtual cores. The actual cores on the cloud can be much less. And on top of that, we don't know if the cloud provider oversubscribes the machines. So this was not the right solution for us. We had to dig further. We had to identify the dominant cost inside Hyperq that contributes to the overhead that the client sees. And we instrumented the code to get some more granular timing information. And we wired off operations in order to identify the costly steps inside Hyperq. The steps we are focusing on are fetching the data from the cloud database engine, converting the data, spilling the data to disk during conversion if the memory is limited, and sending the data back to the client. During this process, we identified that the data conversion part, the data we receive from the cloud before we send it to the client, converting this data was the dominant cost. Wiring off the data conversion, we noticed that Hyperq, the overhead of fetching the data, inserting and sending the data back to the client was not much lower. It was only 20% slower than using a SQLite command, which is a well-known utility to execute tasks on database. So the question that we asked ourselves is, how do we make the data conversion step faster? And we typically start by profiling the code. We want to know how many times each function is called and what is the time we spend in those functions. We used all three. We used the Erlang profilers. I believe most of you are familiar with those. cprof will return how many times its function is called by all processes. eprof will return the same information along with how much time we spent in those functions, but the output will be organized by process. And the fprof keeps track of the function calls, and it will give the callers and the called function by each function. Now, because this profiling phase can have multiple iterations, because we profile once, we identify some problematic functions, we improve them, and then we need to profile another time to get the updated output from the profilers. We need easily repeatable experiment for that. In our case, this was a simple select statement that would return the same amount of data as the customer query. The goal during the profiling phase is to make sure that we get the expected number of function calls. In our case, we knew that we had to convert more than 300 million of elements. So if we see that a function is getting called much more times than that, then clearly something is wrong. And we also, the second goal was to detect the expensive functions and try to optimize them. So we start with cprof. cprof will help us with the first goal, to make sure that we get the expected number of function calls. The screenshot here shows a sample of the output of cprof that we got after profiling the HyperQ code, and on top is the function that is getting most of the times. It's the function doFlatten. Then we move to eprof. eprof, as I mentioned earlier, it will organize the processes, it will organize the output by processes. This is very useful for us because we want to focus on the processes that perform the data conversion. The screenshot on the left is how the output organized by process look like, and on the right is a sample of the output for a process that performs data conversion. And at this time, at the bottom of the screenshot, we see the same function, the doFlatten function, that is the one called most of the times during data conversion. So after running cprof and eprof, we know what functions are expensive and what functions we can try to improve. However, not all functions are written by us. Like the doFlatten is not written by us as part of HyperQ. So then we need to move to fprof. fprof, as I said, it will keep track of what functions are being called by what functions. The output is organized by sections where for each section there is a subject function. The subject function is marked with a percentage character you see on these two screenshots on the right side. So on the screenshot on top, the subject function is the doFlatten function. And the rows above the subject function are the callers, and the rows below are the called functions. And as you can see, the doFlatten is getting called by itself as part of some recursion, and it's also called by another function which is called flatten. Now, next we need to move to the section where the function flatten is the subject function. And this is what we saw on the screenshot below. And among the callers of the function flatten, we can start seeing some functions that we wrote as part of hyperq. And in this talk, we will focus on the function format date. I have an example here of this function. The two screenshots on top is the function before any optimization. So this function will take two arguments. The arguments are shown on in the first bullet. It's a format for a date and a date value. The function will call a helper function that will produce pairs of IO-lib formats and some values. These pairs are shown in the second bullet. And then we used to call unzip on these pairs to separate the formats and the values. Then we call flatten on the formats, and then we end up calling IO-lib format in order to generate the desired output, which is shown in the third bullet. And the output is the date based on the given format. So now I would argue that this is probably a beautiful function. But is it fast? Really, it's not fast based on what profilers told us. So we tried to refactor this function. We tried to get rid of the calls of the function flatten that appears to be slow for us. And we refactored the helper function in a way to directly produce the final result by appending the values we need into a list. So after doing that, we wanted to capture the improvement that we could get. We tried to format 1 million dates. Before any optimizations, we used to spend 12,000 milliseconds to format 1 million dates. And after refactoring the helper function, we improved the execution time. And the execution time was dropped to 758 milliseconds. And I will share some takeaways from the profiling phase. A process that worked for us was to run cprof and eprof as part of using the original data. The output from cprof and eprof was helpful to identify the expensive functions. And then we ran fprof, and then we walked through the function calls to find what are the actual functions we need to optimize. Now, fprof, I need to mention that the fprof is much slower than cprof and eprof to run with high overhead. So if you ever plan to try something similar, worth using a much smaller data set of the original data for fprof. In our case, using a smaller data set, this didn't really affect the whole process because the call tree remains the same, independent of the size of the input. And this concludes our profiling phase, but we realized that not all optimization opportunities can be found with profilers. And in the next part of the talk, Marc will walk us through some of these optimizations.
Yeah. So some, like Niko was saying, some optimizations or opportunities for optimizations aren't easily found with profiling. And so one of these was trying to optimize our use of binaries. We couldn't see these in the profiles because this kind of optimization work is more diffuse through the code. And in order to, so maybe we could see it by the timings of the functions, but in order to understand that, we'd have to know what good versus bad is, right? We just have a number, but if we don't know how much of an improvement or that we're doing something wrong, what the detriment is, we can't use the profile to really identify that. But the compiler helps us with this bin opt info flag, where it will produce warnings that show sort of both the good news and the bad news, right? It will tell us where optimizations are being applied and where optimizations are not applied, and a hint as to what the problem was. I did also notice that there were cases where it would miss some opportunities. So this can be an iterative process where you kind of go through and fix some of these and then rerun the compile with this option to, and then more would be revealed. And so once we discovered that we had opportunities to do these kinds of optimizations, we started running simple experiments. And the details of the code are not terribly important, but the idea is that rather than trying to test this against the hypercube directly, we wrote small sample programs and a very simple test harness to try to simulate what the structure of the code was. So this slide shows the general idea of how the code was structured, where we have a large binary and we're decoding the head of that binary in little chunks and returning those chunks. So we tried a bunch of different experiments to see how we could potentially improve the performance of the decoding. So in one example, for example, we tried replacing the function call that does the decode with doing the decode inline, and we saw some improvement there. We also tried things like, well, what if you add pattern matching on the binary so that the compiler understands that the first argument is a binary. And this turned out to help quite a bit, probably much more than many of the other experiments that we tried, right? And notice that this also applied even to the catch-all, right? If you didn't do it in the catch-all, then the compiler wouldn't know that the first argument had to be a binary, and the optimization went away. Another example of something that we tried was to, instead of the decoder splitting off, sort of returning, the decoded part and what was remaining of the binary, if it returned the length and that slicing happened in the calling function, that also significantly improved the performance of the decoders. So overall, we came up with some takeaways on how to better write our code for this. We should focus on trying to use a local function for the decoding, not return the rest of the binary, just return the length, add pattern matching for binaries where appropriate, but don't put them where they're inappropriate, because that tended to slow things down a little bit. And then we weren't quite sure. We did some experiments with checking to see if the guard was any better than the pattern match, and it was a little unclear. It seemed like if you did the pattern match, maybe it was a little bit better, but we're not absolutely sure about that. So Niko will now just sort of wrap up and summarize how all of these optimizations really helped us.
Yeah, so after we tried several optimizations, we ran a bunch of experiments and see the impact of the optimizations. Here I'm sharing a simple experiment where we are running a query that returns the same amount of data as the customer query. Hyperq is running on a 32-core machine. The execution time for this query before an optimization was 300 milliseconds. And
300 seconds.
300 seconds. And after any optimization, the execution time dropped to 181 seconds. And this is a 40% improvement. The throughput increased significantly. We are now converting data in a much higher rate. The CPU utilization dropped half. and the degree of parallelism also dropped significantly. The degree of parallelism is on average how many chunks we convert at the same time in parallel. Now, this drop in the degree of parallelism might not be very intuitive, so I have an example here to explain that. The rate of which we receive the data from the cloud doesn't change. No matter what optimization we try, we will receive the first chunk of data at time t1, the second chunk of data at time t2, and the third one at t3. Now, before any optimizations where the conversion took longer, all three processes that would convert the three chunks would overlap. That would give a degree of parallelism closer to 3. But after the optimizations, it's likely that we are done converting the first chunk before the third chunk arrives. So this will give us a degree of parallelism no more than 2. And here I have a summary of all the optimizations we have tried. We covered the first 2 bullets in this talk. Some more optimizations we tried is we tried similar optimizations similar to the date optimizations that I showed earlier. We tried something similar for text and numeric data types. We made sure that we have enabled Erlang 24 with JIT. During this process, we realized that our development environment was using GCC, a version of GCC that was not supporting compiling Erlang with JIT. And we tried, we wrote a couple of NIF-based implementations for some functions that were used quite often in our code. And before we conclude, we'll share some next steps that we can take. As the data conversion becomes faster, we probably need to reconsider our bottlenecks. We probably need to pay closer attention to the other steps in HyperQ, steps of fetching the data from the cloud database engine, spilling the data to the disk, or sending the data back to the client. And we also want to focus on our memory consumption. We have seen that during conversion, our memory footprint is pretty large. And with that, we are happy to take any questions you might have.
Any questions here?
You said that you're trying to put what approach did you
Oh, okay, so the question was about the NIFs? Yeah, so the question was about the NIFs. Yeah, what approach did we take with writing the NIFs? So we looked at the profiles and identified some functions that we basically couldn't optimize in Erlang. And in particular, the string, in order to convert the data, we need to know what the string lengths are. So we were calling string length a lot. And that function in the string module in Erlang is actually quite slow, particularly if it's a Unicode string, Unicode encoded string. So we made the decision to try to write that in C as a NIF. In some ways, it's a fairly simple NIF to write because we made a number of assumptions, like, it was a binary that was coming in, and that you're just returning an integer, which is a pretty easy thing to write also. And then when we retested it, that showed a really significant improvement in computing the length of the string, because the Erlang function is tail recursive, and it has to decode each byte differently. The other function, we were a little bit more on the fence on, the data conversion to return a row of data, the header to it is a bitmap to say which of the columns has a null value, right? And there was some complicated code in Erlang to build the bit string and then round it off to the right length and do some other stuff. And we thought, well, maybe we should just try to do this in C because that's a much more natural thing to do in C is the bit mapping. It in some ways it simplified the Erlang code because then we didn't have to maintain two different lists of things of which are the columns that are null and the converted values. And so I think that was more about looking for opportunities to refactor the Erlang code to just make it a little bit simpler by just moving something into a NIF into C. Yeah, I don't know if that helped. Yeah, okay, terrific. Any other questions? Anything? We can't see if there's anyone typed a question, so the host may have to help us with that. And I also don't know how much more time we have, so.
You mentioned saying a lot of problems, but you also experiment with
Yeah, so the question is, did we experiment with parse transforms? Yeah, or anything like that? Yeah, no, we didn't. We did not try that. Although I think that there might be some opportunities in other parts of our code to do this. So for example, when we do the translation of the SQL, one of the things that we end up producing these very large tuple data structures that represent basically the parse tree. And they can be because some of the queries come in, there's maybe sometimes the SQL is 2 or 3 megabytes of SQL text. They turn into giant trees, parse trees. And then we want to compare parts of them to see, is there a duplicate part or, we do a transformation and has it changed? And so for a while, what we used to do was just compare the tuples to say, is this tuple equal to this one? But comparing two tuples that are 500 megabytes big, kind of the VM isn't always very happy about that. So we have refactored all of the code, or tried to refactor all of the code to avoid that by passing a flag that said, yes, it's changed, no, it hasn't changed. But there are probably still places in the code where we are doing that, and it would be interesting to try to write a transform that could maybe run in a debug mode that identifies when these records are being compared directly. But I'm not quite sure exactly how we would go about doing that. Yeah.
Ebase has a question. You say ask Ebase to
Right. So Ebase has a question?
Yep. Hi, thank you for the talk. Do you hear me?
Yes, we can hear you.
Okay, so yes, more CPU, more cores doesn't lead to more expected improvement, and that's understandable because usually what happens is a cache contention, because cache level 2 and 3 are shared by the core, and so that made me think: did you actually profile cache misses and stuff like that?
No. So the question was, did we sort of explore at a more hardware level the CPU cache and profile cache misses? No, we did not do that. We do believe that a lot of the impact was due to the hyperthreading, where two virtual cores are sharing one physical core. And so when we're on if we've configured a 32 core system, 32 virtual core system, you're really only getting 16 physical cores. But Erlang, of course, thinks it has 32 cores. So when we were doing some of the profiling and the benchmarking, right, we're getting a degree of parallelism at 20, 25, which means we're oversubscribed for the number of physical cores. So when we increased the number of virtual cores, we didn't see as much of an improvement as we'd hoped to. I think because of this oversubscription on the Erlang side for threads of execution. But that is a good point, and it is something that we could probably look at as the sort of next tier of optimizations. Thank you.